Let's do a little bit of reviewing about Coulomb's law and electric field lines. The electric force between two charged identical metal spheres has the magnitude F. Is F attractive or repulsive? And the answer is it's attractive. One of the charges is positive and the other one is negative, and opposites attract. In terms of F, what will the force be if the distance is reduced to 1/3 of d? It started out as d, and now it's reduced to 1/3. Coulomb's law says that the electric force is equal to K Q1 Q2 over R squared. If the distance is 1/3 of what it was, when you square that, you're going to get 1/9 in the denominator here. And 1/9 in the denominator means that you're going to end up with F is going to be 9 times greater. The closer we bring those charges, that attractive force is going to get stronger and stronger. And if we reduce the distance to 1/3, it will be 9 times stronger. If we want the force to become 1/2 of F, what should the new separation be? If we look at Coulomb's law here, we can see that F is proportional to 1 over R squared, which means that R is proportional to 1 over the square root of F. Well, that means that we have a 1/2 in the denominator here. And 1 over the square root of 1/2 is the same thing as the square root of 2. So the new separation, root 2 larger. And that makes sense in some way. If there's a greater distance, the force should be less. We're going to take these spheres and we're going to touch them together, and then we're going to pull them apart again to their original distance. How much charge will reside on each one? If these two spheres are identical, which we're told they are, that means that they are going to reach equilibrium with each other. And the total amount of charge here is negative 9q plus 3q. That's negative 6q, which means we're going to get negative 3q on each of the spheres. That would not be the case if these had different radii, but they have the same radius. After part D, will the force between the spheres be attractive or repulsive? Repulsive, because one of the charges is negative and so is the other. In terms of the original force, what will the magnitude of the new force be between the spheres? Let's look once again at Coulomb's law, which says that the electric force is equal to K times 1q times the other q divided by the distance squared. In the first case, one of the q's had a magnitude of 9. You can see that at the top of the screen. The other one had a magnitude of 3. In the case now, one of them has a magnitude of 3, and so does the other. The value of R is the same. So that means that this has 3 times the electric force that one does. What will be the magnitude of the new force compared to the original? 1/3 of the original force. And it'll be repulsive, but the magnitude will be 1/3. Here we have 3 charges, and the electric field lines are shown here. And we want to first determine the sign and the relative magnitudes of these charges. I look at the diagram here. It might be hard for you to see in the video, but charge A has field lines running away from it. Therefore, it's a positive charge. B also has field lines running away from it, so it's a positive charge. But C has field lines terminating on it, so it's a negative charge. The magnitude of the charges can be understood in terms of the number of field lines that are either originating or terminating on each charge. And I'm not going to do this in the video, but if you were to count these up, charge A has 20 field lines originating on it. Charge B has 26 originating on it, and C has 29 terminating on it. So in terms of the charge magnitude, C has the greatest charge magnitude, B is slightly less in magnitude, and A has the lowest magnitude. Let's take that same picture and let's take point X, and we're going to draw a circle in there that's about as big as I've showed there at the top of the screen. That's supposed to be a circle. This circle represents a neutral metal sphere that's right there. Letter C, let's draw several positive and negative signs on the circle. You can see in this general region, the field lines from A, they are going to terminate on this conductor. So that means I'm going to have negative charges on that side of object X, and I'm going to have positives on this side, and I'm going to have the same number because we're told that this object is neutral. Once again, how did this happen? These conduction electrons moved towards charge A, uncovering these positive charges. The positive charges have not moved. It's the negative charges that have moved. Is there a net electric force on the metal sphere at this point? And the answer is yes. There will be a net attraction towards charge A. And the reason for that is these 4 negative charges are attracted with a little bit of a stronger force than these 4 positive charges are repelled.